What if an AI model could have a trillion parameters, yet think as fast as one with only 37 billion? That's not science fiction, that's mixture of experts, the architecture quietly powering almost every frontier AI model you use today, from DeepSeek to Gemini to GPT-4. In this video we will go deep, the history, the math, the full architecture, every component, and how the field has evolved all the way through 2026. Let's go. Let's start with an analogy. Imagine a hospital. When you walk in with a broken leg, the hospital doesn't make every doctor examine you. It routes you to the orthopedic surgeon. The cardiologist, the neurologist, the dermatologist, they stay idle. That's exactly how mixture of experts works inside a neural network. The model contains many expert subnetworks. For each token the model processes, a router decides which small set of experts to activate. The rest stay dormant. You get the knowledge of a massive model, at the compute cost of a much smaller one. Before going into the architecture, we must understand why we need MoE in the first place. A traditional dense model activates every single parameter for every single token. Want to double model quality? You roughly double the compute cost. That's O of N scaling, brutal. By 2020, state-of-the-art models needed hundreds of millions of dollars to train. In Palm 540B, an enormous dense model, 90% of parameters live in feed-forward layers, and every one of them fires for every token. Wasteful. MoE breaks this. With sparse activation, you keep all the parameters in memory, but you only compute on a small subset, typically 2 to 8 experts out of dozens or hundreds. The result? Train a trillion parameter model for the compute cost of a 37 billion one. That's the fundamental promise, and it delivers. Now let's see exactly where MoE fits inside a transformer. A standard transformer block has two sublayers. First, multi-head self-attention, which lets every token attend to every other token. Second, a feed-forward network, two linear layers with a nonlinearity in between, applied independently to each token position. In a dense model this FFN is always the same for every token. In a MoE transformer, we replace that single FFN with a bank of n expert FFNs, plus a router that chooses which experts handle each token. Attention stays dense, it's still computed the same way. Only the FFN layer becomes sparse. This is important, the attention mechanism is untouched. Only the feed-forward layers gain the mixture of expert structure. Now let's zoom into the expert itself. Each expert in a MoE layer is a feed-forward network. Let's understand what that means precisely. The FFN takes an input vector x, the token representation, of dimension d model. It first projects up into a higher dimensional hidden space of size DFF, typically 4 times d model. This projection is a learned weight matrix W1, plus a bias B1, followed by a nonlinear activation function. Modern transformers usually use SWI-GLU or GLU, both smoother than the old ReLU. Then it projects back down to d-model dimension with weight matrix W2 and bias B2. That's it. 2 linear projections with a nonlinearity between them. In GPT-2 for example, d-model is 768 and DFF is 3072, a 4x expansion. In Mixtral 8x7b, each expert FFN has d-model 4096 and DFF 14336. The genius of MoE. Instead of one big FFN, you have n smaller FFNs, each trained to specialize in different kinds of knowledge. The router, also called the gating network, is the brain of the MoE system. It decides, for every token, which experts to activate. Let's go step by step through how it works. Step 1, the input token vector x is multiplied by a learned weight matrix W_G. This produces n raw scores, 1 for each expert. Step 2, a softmax is applied to get normalized probabilities across all experts. Step 3, we pick the top k highest probabilities. Typically k equals 1 or 2. Step 4, only those top k experts process the token. Their outputs are multiplied by the softmax probability and summed together. Mathematically, the output equals the sum over selected experts I, of softmax score I times expert I applied to x. The weight matrix W_G is small, it has n rows and d-model columns, where n is just the number of experts. So routing adds minimal overhead. One critical challenge: the router can collapse, repeatedly choosing the same experts. This creates hot experts and cold experts, destroying the specialization benefit. To fix this, MoE training adds an auxiliary load balancing loss that penalizes unequal expert utilization. DeepSeek v3 took a different approach, bias-based routing, adding a small learnable bias to router scores so experts are used more evenly without needing an auxiliary loss term. Let's now put everything together in one diagram showing the full MoE layer. A sequence of tokens enters, let's say, the capital of France. Each token is processed independently through the MoE layer. The token vector X goes into the router. The router computes scores for all n experts, say 8 experts in Mixtral, or 256 experts in DeepSeek v3. Top K are selected, say expert 3 and expert 7. Only those two FFNs receive X and compute their output. The outputs are weighted by the softmax scores and added together. The remaining 6 experts, or 254 in the DeepSeek case, do zero computation. They just sit in memory and used for this token. This is called sparse conditional computation. Different tokens might activate completely different experts. Interestingly, researchers have found that experts do develop genuine specialization. Some experts handle syntax and grammar. Others handle factual knowledge. Others activate on specific languages or domains like code or math. This emergent specialization is one of the most exciting properties of MoE. One key challenge in MoE is load balancing. If the router isn't trained carefully, it might send most tokens to just a few experts, leaving others almost completely idle. This is called routing collapse. The solution: add a special loss term during training that rewards even distribution of tokens across all experts. This ensures every expert gets used and learns something useful. Let's look at some real modern MoE models. Mixtral 8x7b was the first mainstream open-source MoE model. It has 47 billion total parameters but only 13 billion active per token, using 8 experts and activating 2 at a time. DeepSeek v3 is the most impressive example, 671 billion total parameters, but only 37 billion active per token. It uses 256 experts and activates 8 at once. It was trained for just $5.6 million, a fraction of what GPT-4 cost. Today, nearly all frontier models like GPT-4, Gemini, and Claude are believed to use MoE. Running MoE models at Inference has one main challenge: you need all expert weights in memory, but only compute a few per token. The solution is quantization, using fewer bits per parameter. For example, Mixtral 8x7b in 4-bit quantization fits in about 24 GB of VRAM, which runs on a single high-end consumer GPU. With the right setup, MoE gives you large model intelligence at small model speed. To wrap up, mixture of experts is a fundamental idea in AI. Instead of activating all parameters for every input, MoE uses a router to send each token to only the most relevant experts. This gives you massive model capacity with efficient compute. From the hospital analogy to real models like Mixtral and DeepSeek v3, MoE has proven to be the standard for frontier AI models. It's not just an optimization, it's a different way of thinking about neural networks.